Hello everyone. Today we're continuing with solving trig equations. Essentially what we've been doing for the past few weeks, but with a few extra steps as we make the equations a little more complex. The end result is still the same. We are still going to be referring to our unit circles. We are still trying to solve to isolate variables, and we're still usually talking about a limited domain or limited period of 0 to 2 pi. So, in general, we're going to substitute as desired or needed. There are other variables aside from x and theta, and sometimes a little substitution can turn a complex-looking problem into a simpler-looking problem. Once we're happy with how the problem looks, we're going to follow our algebraic processes. I mean our PEMDAS, essentially. Please excuse my dear Aunt Sally. Our order of operations. We're going to keep doing that until we need to use some sort of algebraic equation. Maybe it's going to be Pythag. Maybe we'll have to do some foiling or some factoring or some, what else is there? Quadratic formula. Whatever we need to do. At the end, once we get our variable isolated on one side and some value on the other, we're essentially going to look at our unit circle. The same unit circle we've been using for the last 4 months. Find the corresponding coordinates or measurements on the unit circle, and that's going to be the angle that's going to be your solution. And I know some people don't like when we do our trig functions because sine, cosine, tangent, cosecant, secant, cotangent looks scary. You've got multiple letters in there, and our brains think they are all separate variables. Just remember, those are trig functions, not individual variables. But let's try to put your minds at ease. Let's say, for instance, I asked you to solve the equation 2x plus 3 equals 2. Our first step would be to subtract 3 from both sides, such that we have 2x is equal to negative 1. We would then divide both sides by 2 to give us x is equal to negative 1/2. Easy, right? Now suppose I wanted you to instead solve 2 sine of theta plus 3 equals 2. We're going to follow the same process. We're still going to subtract 3 from both sides, giving us 2 sine of theta is equal to negative 1. I'm still going to divide both sides by 2, which will give me sine of theta is equal to negative 1/2. And now just look at my unit circle to find out what thetas have a sine of negative 1/2. According to my unit circle, this occurs 2 places. This occurs at 7 pi over 6 and at 11 pi over 6. And that's all. So suppose instead we were looking at quadratics, and I wanted you to solve for 2x squared minus 1 equals 0. Our first step would be to add 1 to both sides to give us 2x squared is equal to 1. Divide both sides by 2. X squared equals 1/2. Take the square root of both sides. That would be x is equal to plus or minus the square root of 1/2. We'd then have to rationalize that a little bit because we don't want to have square roots in denominators. So rationalization process, we still have our x, still going to be equal to plus or minus square root of 1 over square root of 2, which would become plus or minus 1 over square root of 2, which would then rationalize by multiplying the top and bottom by the square root of 2 over square root of 2, which would then give us plus or minus the square root of 2 over 2 as our final x answer. Suppose then I wanted you to solve for 2 sine squared of theta minus 1 equals 0. Well, first things first, add 1 to both sides. So 2 sine of theta is equal to 1. Oh, sine squared is equal to 1. Divide both sides by 2. Sine squared theta is equal to 1/2. I want to take the square root of both sides. That's going to be sine of theta is equal to plus or minus the square root of 1/2, which we've seen from the previous slide is equivalent to plus or minus root 2 over 2. Well, for what thetas do we have a sine value that is either going to be positive root 2 over 2 or negative root 2 over 2? This occurs 4 places. This occurs at theta equals pi over 4, theta equals 3 pi over 4, theta equals 5 pi over 4, and theta equals 7 pi over 4. And that's that. Suppose I wanted you to solve for 4x squared minus 3 equals 0. First step, add 3 to both sides. So 4x squared equals 3. Divide both sides by 4. X squared equals 3 over 4. Square root of both sides. X is equal to the square root of 3 over 4, which we would rewrite as square root of 3 over square root of 4. Still plus or minuses, which would simplify out to square root of 3 over 2. That's what x would equal to make that a true statement. So suppose instead I asked you to solve for 4 cosine squared of theta minus 3. Once more, same process as the previous slide. We're going to add 3 to both sides. So 4 cosine squared of theta equals 3. Divide both sides by 4. Cosine squared of theta equals 3 over 4. Take the square root of both sides. Cosine of theta is equal to plus or minus square root of 3 over 4, which we know from the previous slide will eventually give us plus or minus the square root of 3 over 2. So now, based on our unit circle, what coordinates of theta, or what angles of theta, will give us the coordinates of positive root 3 over 2 or negative root 3 over 2? There are going to be 4 of them. These are going to occur at theta is equal to pi over 6. Theta is equal to 5 pi over 6. Theta is equal to 7 pi over 6. And theta is equal to 11 pi over 6. 4 steps there. Now what if we had a funky looking equation? 2x to the 4th power minus 3x squared plus 1 equals 0. Well, this is where that first step of substitution comes in if needed or desired. Because I myself, I don't like working with any powers larger than, well, 2 if I can avoid it. So what I'm going to do real quick is say that h, some variable that I'm pulling out of thin air, is going to be equal to x squared. This allows me to rewrite this equation as 2h squared minus 3h plus 1 equals 0. Since I've now put it into a quadratic form, I can use my quadratic formula to solve this out, such that h is going to be equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Plugging in what I know, h is going to be equal to 3 plus or minus the square root of 9 minus 8 all over 4. Or h is equal to 3 plus or minus 1 over 4. Therefore, we're going to have either 1 or 1/2 as our answers for h. But our original problem was based in x's. So we need to make one more conversion and go back to our x's. So x squared was equal to h, and h can be 1 or 1/2, which means then that x squared could equal 1, or x squared could equal 1/2. Again, folks, I'm just using algebra at this point, in order of operations. I'm going to take the square root of both sides in each of these. I get x is equal to plus or minus 1. And over here, take the square root. X is equal to plus or minus, well, we've already seen that the square root of 1/2 is essentially equal to square root of 2 over 2, giving us 4 potential solutions of x is equal to plus or minus 1, or x is equal to plus or minus square root of 2 over 2. I bet you can guess what comes next. Solving for cosines to the 4th power. So 2 times cosine to the 4th power of theta minus 3 cosine squared of theta plus 1 equals 0. Once more, I'm going to pull up my variable h. I'm going to say that h is equal to cosine squared of theta. This allows me to rewrite my equation as 2 times h squared minus 3h plus 1 is equal to 0. It's in a quadratic formula format, so I can use my quadratic formula such that the value of h is equal to 3 plus or minus the square root of 9 minus 8 over 4, which, as per the previous slide, breaks down into h is equal to 1 or 1/2. And since h is now cosine squared of theta, we're going to substitute that back in, such that I have cosine squared of theta equals 1, or cosine squared of theta equals 1/2. Take the square root of both sides. Cosine of theta equals plus or minus 1, and cosine of theta equals plus or minus square root of 2 over 2. Well, now I need to look at my unit circle and figure out for what values of theta am I going to get a positive 1, a negative 1, a positive root 2 over 2, or a negative root 2 over 2. And this is going to occur at 6 places. This will occur at pi over 4, at 3 pi over 4, at pi, at 5 pi over 4, 7 pi over 4, and 2 pi. 6 answers, and that's fine. So that's really all we're doing. We're taking our rules from before, substituting to make things easier to look at, following the algebraic processes, using the algebraic equations, and then at the end, going and looking at our unit circle, or at the unit circle worksheet that I gave you way back when. And of course, folks, if you have questions, please ask.